Alright, so this video is over just the basics of electromagnetic waves. And we're going to cover just what it is, which is a fancy word or way of saying light. And we'll cover reflection, refraction, and ray optics a little bit later. So electromagnetic waves. Electromagnetic, that term might clue you into something. It might have to do with something to do with the electricity and something to do with magnetism, electromagnetic waves. And if you remember from a couple of units ago, when we have a wire that's carrying current, then that wire, that current that's flowing, a flowing electricity like that, will create a magnetic field that is going around the wire in such a way, and it's going around the wire in a particular direction depending on the way that the current is actually flowing. So electricity and magnetism are deeply related with each other. One can create the other, just like how we saw that if you have a generator that has a magnet, so let's say we have our south pole here, and we have our north pole here, and we have something like a coil of wire just sitting there spinning in between this magnetic field, then you can actually create a current out of it because you're actually changing the magnetic field within the coil. So a changing electric field or changing electricity can create magnetism, but a changing magnetic field can create electricity. So keeping that in mind, if we take a look at what electromagnetic waves are, they are actually a merger of the electric field and the magnetic field. The electric field will oscillate up and down, or becoming zero and then maximum and zero and then minimum. And while that electric field is changing, it is creating a magnetic field as well. Okay, and that magnetic field will oscillate, and take a look at this. It's actually kind of interesting. It is perpendicular to the electric field, which we've already kind of seen with that whole current carrying wire. Right, the wire goes in a particular direction, and the magnetic field circles around it in a plane that's perpendicular to the wire. So as the electric field changes, it creates a magnetic field. As the magnetic field changes, it recreates the electric field. So the electric field and magnetic field, which are related to each other, is exactly what this whole light thing is. And it's self-propagating. In this type of wave, it's a transverse wave, as you can see, but it's not really moving particles. It's self-propagating in the fact that the electric field creates the magnetic field, which recreates the electric field and goes back and forth, back and forth. And this particular wave, since it doesn't actually need a medium, it's not vibrating any type of particle, is something that can move through empty space. And how do we know that? Well, empty space has no medium to it, and yet we can still get light from the sun. Okay? Now, depending on what wavelength you're talking about with light, you can be talking about a number of different things. You can say that light comes in many different flavors, and it's not necessarily just the colors that we see. That's actually a very small section of the light that we can actually see. Very, very short wavelengths of light are 0.01 nanometers. This is what we would say are gamma rays. Gamma rays, we'll talk a little bit more when we talk about nuclear stuff, but gamma rays come from changes within the nucleus of an atom. Then if you've ever broken a bone or anything like that, you'll go in and get an X-ray. X-rays are a form of light that are really easy to penetrate skin, but not so much to penetrate bone. Okay. After that, we get something that's called ultraviolet. Okay, this means beyond violet or above violet. And this is sitting right next to our visible spectrum. The visible spectrum starts with 400 nanometers and goes all the way to 700 nanometers. This right here are the particular wavelengths that we can actually see. Okay, there's frequencies that are going with these as well, and we'll get to that here in a second. But this right here is the only stretch of the what we call electromagnetic spectrum that we can see. Okay, that's the only part of it. And we have meters that allow us to see things. We have ways to visualize X-rays by photographing or using photographic paper that will show you where an X-ray will hit or where it's blocked. We have ultraviolet cameras that can take a look at that particular type of the spectrum and just shift it into the frequencies that we can see. Beyond the red, we have what is known as infrared. Okay, that's below red. And then on the opposite end, we have radio waves. Now, radio waves you might think are sound, but they're not sound. Sound is sound. Longitudinal waves is sound. But the radio waves that are transmitted are actually a form of light. Your radio, what it's doing is it's converting light into sound. It's called a radio because it will hear or decode, I guess is a better word for it, will decode information that's hidden in the radio waves, the light waves that it's getting. So it's really just a big translator from light into sound. So radio, you want to make sure you understand radio is actually light. Okay, light is a funny thing in that it can vibrate in any way that it wants to. Much like we did with the slinky in class, is that it can vibrate up and down, it can vibrate side to side, it can vibrate at some random angle if I'm looking at it here, or it can do this angle, or it can go up and down, or side to side. Okay, it can vibrate in any particular direction. So we have this idea of polarization, which we've actually heard this term before in a slightly different capacity. Polarization is something like what we've seen before, a separation of charges, right? We have negatives over here, positives over here, and that's polarizing something, or a polar atom is a separation of charges. This one is a slightly different connotation. It's the same word, it means something a little bit different. A polarization is saying, all right, if light is in fact vibrating in all these different directions, then we can use a polarizer, or we can polarize light, and what we say is, well, we're going to take out all of the different forms of light that are not vibrating in the particular direction. I don't know why this isn't staying. All right, so we'll say we're only going to select the one that is going this way. And you can think about it as it's like a picket fence kind of, where it's blocking out anything that's going to hit the picket fences. It only lets what's going through the slat through, only the light that's vibrating in that particular direction. Okay, that's polarizers. Now you might be familiar with polarized sunglasses, and they have polarizing film on there to take out some of the light. The light that's coming from the sun is unpolarized. It vibrates in all the different directions. And if it hits something and comes to you, for one, water's pretty good at polarizing some of it, but then your sunglasses that have the polarizing filters in it will polarize the rest of it, or just really takes down the amount of light. Another place that we see polarization, and you might not believe me, but think back, if you've ever gone to a 3D movie. Okay, and we're not talking about one of those red-blue movies that you used to be able to go to for 3D. The newer movies, if you take a look at the 3D glasses, they're no longer red and blue. They look like they might be lined or something. And what's actually happening is that you have two different polarizations on your eyeglasses, so that one of the images that's broadcasted can go through one eye, and the other image that's broadcasted can go through the other eye. So this is an area where you have polarizing filters as well. Okay, polarizers are really good for just blocking out light. You can have polarized windshields and things like that. And all of that has to do with the idea of blocking out some of the light just by physically not letting it through if it's vibrating in the wrong direction. Remember that you can stop this at any time or rewind it. And the speed of light. The speed of light is something very, very big. We've actually seen it once before. It's 3 times 10 to the 8 meters per second, or 300 million meters per second. The letter that we usually give to this is the lowercase letter c. We've seen this back in special relativity. So with the equation for velocity, v equals lambda f, we can just usually say it's c. C equals lambda f for light. So if we do a problem with this, let's say we take a look at red light. Red light has 700 nanometers in its frequency, or excuse me, its wavelength. And we want to know what the frequency is. So we start off with c is equal to lambda f, and we solve this for frequency, so that's c divided by lambda. And if we plug in the numbers, 3 times 10 to the 8 meters per second is the speed of light, and we're going to divide that by not just 700, because we don't like nanometers, we want to work in meters, so it's 700 times 10 to the negative 9th meters. And when you put that into the calculator, I'm just going to throw it up on the PowerPoint, you end up getting with this horrible number of 4.286 times 10 to the 14 hertz. So in light, we sometimes talk about it in terms of the wavelength just because it seems to be an easier number to talk about. Think about 4.286 times 10 to the 14th. That's this 4 with 13 more decimal places. And move this decimal 13 times. And then we have the wavelength. The purple light is around 400 nanometers. What is the frequency of this purple light? You can do the exact same thing. And if you notice that it comes out to be 7.5 times 10 to the 14 hertz. So here's a question for you. If the frequency is going up, as the last time it was 4 point something times 10 to the 14th, this one's 7 point something times 10 to the 14th, what has happened to the wavelength? Okay, I'm going to leave that as a question for you to answer. Frequency is going up, what happens to the wavelength? Okay, we're going to talk about reflection in class, but I'm going to leave you with this diagram to take a look at. The law of reflection is the angle of incidence, which is actually this angle right here, is always equal to the angle of reflection right here. And you can use basic geometry to verify that with yourself. So we will see you next time.